Hello everybody, this is Statistical Computing and Machine Learning. Professor Zabaras is speaking. So before we continue with the fully Bayesian version of our model for regression, I wanted to spend a very small time to discuss about what is called the Bias-Variance Decomposition or tradeoff. This is a non-Bayesian setting here, what we're looking in the lecture today, but I wanted to review it because it sort of it comes up both in textbooks and papers, and it is relevant to what we're discussing in the context of regularization. All right, so let's see some of the topics we're going to cover. We will discuss about the bias variance decomposition and trade-off. We will of course, discuss all of this in the context of regularization for regression models, and I'm going to give you some examples for that. We will actually use this bias variance trade-off for selecting the regularization parameter. And so the goals for today basically are to understand what this bias variance decomposition is, to understand what a regression loss is, because that's from where we're going to start calculating things to derive this decomposition. And of course, at the end, I'm going to give you some Monte Carlo estimates for the bias and the variance so you can implement this in practice. And we will see one example on how to fine-tune the regularization parameter based on these values of the bias and the variance. Okay. So let me start, with where we stopped in the last few lectures. We notice that when we have regression models that have many more parameters than data, then we overfit. So in the notation of the earlier lectures, if m is much bigger than n, so m is the number of our basis functions or the number of the regression coefficients, and n is the number of data points. So if m is much greater than n, we overfit. Okay, so effectively the only way to address this problem is to control the complexity of the model. So we could not use a complex model in the case of limited data, and that was not very desirable. So what we did is we tried to introduce regularization as the means to control the effective complexity that the model can afford for the given data set. And so today we will try sort of to go a little bit deeper in that analysis and discuss about this bias variance decomposition. Since, the Bayesian analysis is going to wait for another lecture, let me just say that in the context of doing Bayesian analysis, none of these issues of m greater than n leading to overfitting is present in a Bayesian setting. And the reason again for that has to do with the fact that if you think of the predictive distribution in a Bayesian setting, it's an integral over the parameter space of the likelihood times the posterior. And effectively what you're doing in a Bayesian setting, even if you have thousands of parameters, you integrate them out, and as a result, you don't get any overfitting. Okay, so in some sense, we are going to remain on the fully frequentist setting for the lecture today, and we anticipate many of the issues discussed today not to be as relevant when we discuss the Bayesian setting. Okay. So let me start by defining what I call the loss function. Okay, so we have some observations t, and we are trying to find a function y of x to minimize this quadratic loss function. As I indicated in another lecture, you can have other loss functions. We have seen the 0, 1 loss function. We have seen an absolute value of y of x minus t, maybe so an L1 type of loss function. But right now, what we have is we have a quadratic loss function. Now, what we need is we need to define, because both x and t come from their appropriate distributions, we need to discuss the expected loss, and the expected loss will be of this form where we average with the underlying joint distribution of x and t. Okay, so this is the expected loss, and effectively what we're looking to find a y of x so that it minimizes this quadratic expected loss. Now it turns out, okay, that if you solve this optimization problem, that the optimal solution to this problem is the following regression function. It turns out that the optimal y of x, it is the expected value of t given x. Okay, this is very, very important to remember that for quadratic loss, basically you get this mean of the distribution of t given x. Later on, we will see this in the context of Bayesian predictions. Basically, we're going to have something very similar, but the optimal solution is the expected value of t given x. So this is the optimal desirable regression function. Okay, so let me do some calculations now by using this optimal regression function. So what I'm going to do is I'm going to take this my loss function. I'm going to take this y minus t square, and I'm going to add and subtract the optimal regression function, which is this expected value of t given x. So I subtracted it and added it, so nothing major. And I'm going to use that the probability of x and t, the joint, is the conditional times the probability of x, okay, and again nothing major. So if you plug in this expression inside the expected loss and you substitute the joint probability of x and t with the conditional times p of x, what you will get is you will get three terms. One term will come by taking this term square, another term will come by taking this term square, and then you're going to have another term that involves 2 times this first parenthesis times the second parenthesis. Now actually, if you pay attention, the term that involves 2 times the first parenthesis times the second, when you average it with respect to the distribution p of t given x, is going to give you a 0, because this is the only term that depends on t. The dependence here on t has disappeared because you have an average, and this is y of x. So effectively what I'm trying to say, without giving you the complete derivations, it's really one line derivation, is that the expected loss consists of these 2 terms, okay? This error that you see here, and I only have the distribution p of x here, and then you have this other error here, that is the expected value of t given x minus t square times the joint of x and t distribution. Okay. To simplify my notation, I am going to take the optimal or desired regression function, this expected value of t given x, and I'm going to call it h of x. So hopefully there is not going to be any confusion. So h of x is the optimal or desired regression function. Okay. So this is what I have done on the first equation. Basically what I did is I used the equation from the bottom of the previous slide, and I just substituted this expectation of t given x with h of x. Now, if you look carefully on the second term, there, you remember we have to minimize this with respect to y. Okay, that's the objective. And if you look on the second term, there is no y. It's independent of y. So in many ways, you can interpret the second term as the minimal achievable value for this expected loss. You cannot basically do any better than this error given by the second integral. Okay, so so this noise, if you like, we're going to leave it there. We're not going to touch it. This is the minimal error that we can anticipate regardless of what method we use. Okay, so now the other term, of course, depends on y of x, right? And so this is the noise. So what usually we will do, for example, in a Bayesian setting, this optimal solution we're going to approximate it, because we cannot compute it exactly, we're going to approximate it with some regression function that has these parameters w, the same way that we have seen this in the frequentist approach in our lectures to regression up to now. But in a Bayesian setting, w is going to be a random variable. So effectively, we're going to put a prior w and we will derive some posterior on w. So my point is, the uncertainties that are coming in the regression function are going to be induced by the uncertainties in w, because w are random variables. Now, in a frequentist setting, if we follow this approach and we parameterize the regression function with w is taking as as a fixed number. So the question is, where are those uncertainties coming in a frequentist approach? Well, I think we have seen this, or I discussed this in passing. The uncertainties that you see in this type of problems in a frequentist setting have to do with the fact that you model or you compute, let's say, the optimal parameters w by optimizing your algorithm using different training data set d. So when you see variability in w and thus variability in the regression function, you have to interpret those as variabilities induced by different training data sets d. And this is what statisticians will call the bootstrap data sets. Okay, so in a frequency setting, in conclusion, the w, if you're going to use a parameterization of the optimal regression function, that parameterization uses deterministic w. So w are not random variables, but the uncertainty in w is perceived as uncertainty induced by the fact that you train the model repeatedly using different data sets d. So as you change the data set, you get another w, and that gives you another regression function, and that's how you see variabilities in regression functions in a frequency setting. So this is actually what I am going to try to do in the remaining of the lecture today. I'm going to take a collection of data sets d, and I'm going to assume that the learning algorithm that I have, whatever that is, it produces a regression function that one function for each data set d. Okay, and I'm going to denote this regression function as y of x, with some indication that this comes from the data set d. Okay, so with that said, let me do some very simple algebra. I am going to run my learning algorithm, and I'm going to compute some regression function y for the data set d, which of course is not going to be the optimal desired h of x, which is, I remind you, the expectation of t given x. So there's going to be some loss. But what I'm going to do is, because I am interested to compare things across a collection of different data sets d, I'm going to remove and add the expectation of this regression function over data sets d. Okay, so if you can see, I have one term here that involves y minus the expectation of y over d, and then I have another term that involves the expectation of y over d minus h of x. So I can combine the first two terms and the last two terms, and take the square of the first two terms, the square of the last two terms, plus 2 times the first two terms, right, times the second two terms. Okay, I am doing these calculations, by the way, for only one x location, right? So I will plug in this shortly on my expected loss, but right now this is how what I have for a given x. Okay. Now, what I'm interested is, so this is the error that I commit when I evaluate, when I come up with a regression function for the data set d using my learning algorithm. So what I would like to do is, I would like to take the expectation of this over all the data sets that I have available to me. So if you take expectations with respect to the data sets d, you're going to have the expectation with respect to the data set of the first term, the expectation of the second term, and then you're going to have the expectation of this last term, which you may notice that is actually 0, because the only place I can take expectation is in the first term. So I'm going to have the expectation with respect to the data set D of y, and minus this expectation will give me a 0. So effectively what I get is, I get the following two terms. I get the expectation of y with respect to my data sets D, okay, minus the optimal, right? This is minus the optimal regression function, the true regression function, if you like. And then I have a variance term because it is an expectation with respect to the data sets D of y minus the expectation of y with respect to D squared. Okay, so I do have a term that it is a bias squared term and a term that is the variance. And now what I can do is I can take all of this and plug it in inside the expected loss that I have before, that accounts for the fact that x and t come from some joint distribution of p and x of t. And this is what we're going to do, right? We're going to plug in, before we had y minus h squared, so we're going to plug in whatever we computed inside the first integral. Remember, there is nothing to do with the last noise term. It stays exactly as it is. There's no way we can optimize that. It will stay there. And then what we get is, we get that the expected loss is a bias squared term, or if you like, an expected bias squared term, and an expected variance plus this noise level. And let me just write those explicitly. So if you plug in what we had before, on the first integral, you will get a bias squared term, you will get a variance term, and of course we have the noise that we did not do anything about, and we don't touch it. Okay? So in principle, because this is the expected loss, we would like to make this bias squared term and plus variance as small as possible. But we will see that somehow there is a competition, there is a trade-off between bias and variance, but hopefully there is a minimum of this bias squared term plus variance, and we will see if actually we can identify this minimum when we work in the context of regularization for our regression problem. Okay, so this is what we have. I mentioned this trade-off between bias and variance. So you can actually think, in an earlier lecture we discussed this high order polynomial with, I think, if I recall, 10 training data points. So we took a polynomial of order 9, so with 10 coefficients. So the polynomial was very flexible, and it was able to actually fit perfectly to all the training data. And so we got 0 training error. All right, so the polynomial was very high complexity, had coefficients, if you remember, that they were negative and positive, but big numbers, okay? So we had high variance in our regression function, but we also had low variance, okay? So when we take all these very flexible regression functions, if we average them over data sets, we get a very smooth regression function. We have very low variance. Now, for the case of models that they are very rigid, so if we fit, for example, our complex data with a straight line, we're going to get a situation where we have very high variance, but we have very low variance. Okay, so there is this trade-off between bias and variance, and of course of interest will be to identify if we can find a minimal for the combined bias squared plus variance term in our expected loss function. Okay. Okay. So again, I remind you that this decomposition, it is really only relevant to a frequency setting, because in a Bayesian setting we only work with one data set. Okay, we don't have multiple data sets. If actually somebody gives you lots of data, you will use all of them to do training of your model. You're not going to do what we discussed today, training the model with different data sets D. So we are not going to do that in a Bayesian setting. So let's go and review our regression problem with quadratic regularization with regularization parameter lambda. So I am going to take the case of a very complex polynomial. So m is equal to 25. And I'm going to assume that I have 25 data points. So you do anticipate, if you don't use regularization, you will actually overfit. Effectively, you will fit things to noise. So let's see what happens, right? So this is the solutions that you see here, especially on the left, are over different data sets. So this is the regression function we will be computing, using different data sets. And I believe we only use, we don't plot all 100 regression functions. We use a very small subset, maybe half or so of the regression functions. Okay, so what you observe for this case, you remember we have the regularization in this case is log of lambda is 2.6. So that's a very high regularization. So if you have a very high regularization, the effective complexity of the model is low. Effectively, that regularization forces a lot of the W's to become 0. So in that case, we have high variance that you can see on the picture on the right. So this is the actual generating function, and this is the average over the 100 data sets of the regression function. So the bias is very high, but you notice the variance is relatively low, as you can see on the picture on the left. All right, so this is for very high regularization. So now let's take some regularization that is low, but not very low. I'm going to show you the very low regularization in one extra slide. So we have some intermediate regularization such that log of lambda is minus 0.31. The rest of the settings identical to what we had before. So obviously you can see now that the model is complex. So we have way higher variance than we had before, but the bias is smaller. Okay, the bias is not 0. It is still there, but you notice in comparison to the previous case, if I can go back, notice how big the bias is here. Here the bias is significantly less. Okay. So let me now use a very low regularization parameter. So log of lambda is minus 2.4. So you can see in this particular case, for such a low regularization, I have very high variance. Okay, but notice if I average over my 100 data sets my regression function, I almost get no bias at all. So you can see this trade-off that we get between bias and variance as we change the regularization parameter. So now you can appreciate why I mentioned many times in earlier lectures that the regularization parameter is the main parameter that controls the effective complexity of the model, or if I can say it is the parameter that effectively adjusts the effective complexity of the model to whatever size training data set you provide to your model. Okay, let's do the following. What we would like to do is, before I show you on if we can minimize this bias squared plus variance term, because that was part of our loss function, let me give you just some Monte Carlo estimates on how you're going to calculate this in practice. So let's say that you have L data sets, so your training algorithm will operate separately on L data sets. So the average regression function that we saw before is computed with the sample average, if you like, and then you can approximate the variance. You notice the variance here requires an integration, it's an average over P of x. So what we're going to do is we're going to take samples of P of x n from P of x, and we're going to use a Monte Carlo approximation of this integral. So the bias square will be 1 over n, the summation over these Monte Carlo samples of my average prediction minus h evaluated at xn square. All right, so this would be the approximation of the bias, and you can do the same thing for the variance. You're going to eventually get a double summation because one comes from sampling P of x, right? So you have capital N samples of P of x, and the other one comes from the approximation of this expectation over data sets. So when you see this calligraphic L indicates samples over data set, and when you see the subscript n indicates basically samples coming from the distribution P of x. So this is how you're going to compute the bias square and the variance in practice. Now let's look at our regression problem. This is exactly the situation, the problem that we have looked in the past, okay? And you can click if you want the MATLAB code to see the details. But what we're doing here is we're plotting the various expected errors versus log of lambda. So on the horizontal axis, we have the log of the regularization parameter. So you can see when the regularization parameter is small, all right? So when the regularization parameter is small, we have very large variance, all right? So that's our overfitting. So this is very large variance here, and you can see that the bias is very small. Okay, so when lambda is very small, okay, you remember the case when we were fitting our 10 data points with a polynomial with of 9th order, right? The polynomial was very wiggly, so we had very high variance. Okay, that's what we have here. But when we average over data sets, the bias is very small. If we go to the other extreme and we have very high lambda, so what we're going to have, effectively, we're going to have a very smooth regression function. We have very small variance, but the bias is going to be very high. Okay, so this is the trade-off between bias squared and variance, and this plot versus of this expected losses versus the log of the regularization parameter is very important because you can use it to actively figure out what is the best value of the regularization parameter that you can use. So what is that parameter that controls and gives you the best effective complexity of the model for a particular data set. So if you notice it is not very clear, but there is a minimum of if you add the variance curve and you add the bias square term, you get this term this curve that you see here, and with the cross here I have indicated the location that effectively has the minimal bias square plus variance. So effectively what you can do is you can select the log lambda for the location where the bias square and variance becomes minimal. And here is an interesting fact for this particular regression problem that we have worked in this and the previous lecture. So this is the sinusoidal data example. We notice that if you compute the root mean square error over a test data set, all right, and details I think I provided in the slides. So if you take this root mean square error over a test data set, so a data set that you have not used to train the model, it appears that the minimum of the test error is about at the same value as the location where the bias square and variance are minimized. So this sounds, very nice fact and a very consistent anticipated sort of result. So In conclusion, you're going to be using log of lambda in the location where you minimize bias square plus variance, and it turns out that that location is the same location that minimizes also the test error over data sets that you have not seen before. Okay, so that's all I wanted to say about this bias-variance decomposition. The only thing I remind you is that it's not of significant or any help in a Bayesian setting that we will start discussing in the lecture tomorrow, simply because in a Bayesian setting we only have one data set to train. We don't have the luxury of computing the the solution of our algorithm over different data sets and then averaging and comparing with respect to this averaging over data sets. All right, so I am going to close here, and we will continue in the next lecture with a Bayesian approach to regression, starting with our standard likelihood model, but putting a prior on it, and we would see some very interesting results that we will get out of that approach, results that effectively will resolve these overfitting issues that we have discussed for the last 2 to 3 lectures. Until then, happy readings. Bye.